So hello Internet and welcome to SyC Chile. Our guest today is Rosemary Pike, astronomer at the Minor Planet Center. Rosemary studies small bodies in our solar system, and she's one of these people who protects us against asteroids. So hello Rosemary.
Hi. Yeah, it's great to be here. So when I work at the Minor Planet Center, one of the things we do is accumulate all the data that people get around the world where they're finding these small bodies, and we compute their orbits and try to determine if any of these are potentially hazardous objects. Mm-hmm. So there have been a few that have actually been predicted to impact the Earth before they actually hit, but they were all very small and burned up in the atmosphere. But it's the goal to try to identify any Earth impactors before impact.
Okay, so far we are safe. Right?
So far we're safe. Yeah, you would probably know if. But if you remember the big event in Chelyabinsk, mm-hmm.
That
is a large object that came in and burned up in the atmosphere, but still caused damage. That one was not predicted ahead of time, so we're trying to get more of them before they actually impact. Because if they're going to actually make it through the atmosphere and hit the Earth, then we'd like to have some warning as to where that will be. So there are small bodies all throughout our solar system. So these are objects that basically don't dominate the space where they are. So if you think about the planets, the giant planets and terrestrial planets, they're large and round. So most small bodies are not round, and they occupy the whole region of our solar system. So there are inner solar system small bodies, and then there's the asteroid belt, which you're probably familiar with, where there are a lot of small bodies, including several large ones. And then out beyond Neptune, there's another large reservoir of small bodies, which we call trans-Neptunian objects. The first TNO that was discovered is actually Pluto, which was discovered in the 1930s by Planetary. But we didn't realize for quite some time that Pluto was a member of a much larger group of objects. So there were some predictions that basically what we see as comets now, the Jupiter family comets, were coming in from a reservoir just beyond Neptune. Mm-hmm. So that was predicted by a couple of people, including Kuiper and Edgeworth and Ip and Fernandez in the 1940s and 50s. But it wasn't until the early 90s that we started actually finding things out there in addition to Pluto. When Pluto wasn't yet known to be part of a group of objects, Pluto was classified as a planet, the same way that Ceres and Vesta in the asteroid belt were classified as a planet before the asteroid belt was fully understood.
So do you want to talk a little bit about what happened?
Yeah, so in 2006, the IAU, which is the International Astronomical Union, sat down and tried to decide what nomenclature they wanted to use within the solar system. So one of the questions was, is Pluto a planet? Because it's a member of this group of small bodies, the same way Ceres and Vesta are a member of the asteroid belt. And so what they decided is that a planet needs to orbit the sun, mm-hmm. And it needs to be large enough that it has made itself round through its own gravitation. And it also needs to have cleared its orbit of other things. So Pluto is around the sun and it is round, but it has not cleared its orbit space of lots of other small objects. So they decided that Pluto would be a member of this group that they made, which is new, which is dwarf planets. So Pluto is now a dwarf planet, which basically is objects which meet the first two criteria.
Why are we so interested about trans-Neptunian objects?
Yeah, so trans-Neptunian objects provide a lot of really interesting clues to how our solar system formed and then how it evolved over time. So these are all out beyond Neptune. So Neptune is at about 30 astronomical units, so 30 times the distance of the Earth from the Sun. And these objects are out beyond that, so they're like 40 to 60 AU is where most of them are. And out there, it's really cold. We're talking, 30 to 50 Kelvin, depending where you actually are in your orbit. And so it's quite cold, and so it preserves a lot of the pristine volatiles in the solar system that are not preserved on inner solar system objects because it's too warm because of the sun. There's also a lot of evidence in these small bodies that there was a large-scale restructuring of the solar system that occurred sometime early in the solar system's history. So basically, a migration of the giant planets. So say Jupiter moved in and Neptune moved out, and this pushed all the small bodies around within the solar system. And there are basically residual signals of this migration in the outer solar system. So where we find TNOs and where we don't find TNOs basically tells us about how Neptune migrated outwards.
Okay. So we're going to be talking about this a little bit more. But before, how do you know what TNOs are made of? I mean, they are still far away.
Yes.
How do you get any information about their composition?
Yeah, so we do have some measurements of what TNOs are made of. So for the large objects that are large enough to be gravitationally round, and they're also brighter, we've identified substances such as methane, nitrogen, ice on the surface, and we find these in spectroscopy. We also see water ice on the surfaces of many TNOs. So we suspect that they're largely, especially the small ones, are primarily composed of water ice and silicates. Okay. But it's very difficult to nail down exactly which ones because the long-term bombardment by cosmic rays has basically almost burned the surface of these objects. So they all look kind of very dark red. So we have had New Horizons recently, which went to Pluto and Arrokoth. We now have geologic mapping and compositional mapping across the surface. So you see things like water ice mountains and nitrogen ice glaciers on the surface. So that gives us an idea of what kind of surface processes might be occurring on a really large trans-Neptunian object. And then it also flew by Arrokoth. Arrokoth is really cool. So it's what we consider a cold classical trans-Neptunian object. And they're called cold classicals because that's sort of what we expected to see. So the sort of classical Kuiper Belt is this idea that there was just another belt like the asteroid belt beyond Neptune. And what we actually see beyond Neptune is a population that is really diverse in terms of orbits and basically puffed up a lot compared to the asteroid belt. So there's a lot more energy in those orbits. And that's sort of where the hot cold comes from. So it's a measure of basically the dynamical energy of the object.
So just to be clear, it has nothing to do with the temperature of these objects.
It's not the temperature. It's basically the energy of the orbits.
Okay.
So that we refer to as hot and cold.
So energetic orbit, what would it look like?
So that would be an object that, say, has a very high inclination. So it comes very far off the sort of the plane of the solar system, which we refer to as the ecliptic. Or it could also be an object where its pericenter is very different from its average orbital position. So it comes much closer to the sun than its sort of average orbit. So Pluto is an example of a very dynamically hot or excited orbit. So it has a high inclination, and it also has a pericenter that's actually inward of Neptune's orbit. So it has a wide range of distances from the sun that it explores, and it also goes high up off the ecliptic plane. And the reason this sort of dynamically hot, cold difference is very interesting is because it tells us about basically how the objects formed and evolved. So the cold classical belt, we think, might actually have formed where we see it today. Okay. So this is sort of low energy, and it's like a thin disk, and everything formed there, and it has stayed there. Whereas objects like Pluto and other dynamically excited objects, we think were actually planted into these orbits during the period of giant planet migration. Yeah, so Arrokoth should be sort of a relic of this very old, very quiescent population. So it's got two lobes, and it looks like basically what we call a contact binary, where we have two objects that form together. So there's been a lot of really interesting simulation work to figure out how we form these sort of merged binary objects, because they have to basically impact each other at very low relative velocities with very little energy in order to preserve the two shapes that are like approximately round, sort of pancakey. So there are two major theories for how planetesimals form. One is sort of pebble-up accretion, where if you imagine you have some small stuff, it clumps together and clumps together and clumps together, and eventually it grows to be planet-sized. So that's one idea. And the other idea that's quite popular is a streaming instability type formation scenario. And when objects form through the streaming instability, you think about the sort of gas and dust disk that existed in the early solar system. As it rotates around the sun and everything sort of drags on everything else, you create these regions of higher density. And if it reaches a threshold density, basically it will collapse the same way that you form a star. And if you form things through the streaming instability, things are born big. If you form through pebble accretion, you'd expect that you have lots of small things and then slightly fewer at the next size. And then as it gets bigger, you have all of the sizes of objects. Whereas if things are formed through streaming instability, they're born big. And then anything you have that's smaller is actually collisional products of these large objects, which were born large, and then they broke apart. So it's really, really interesting to be able to study sort of the population as a whole, which is much more difficult to do with spacecraft, right? Because spacecraft does flybys in very, very high detail of a few objects. And from Earth, what we can do instead is try to look at the bulk population. So one of the populations I've studied a lot is the Plutinos. And so these are objects with orbits like Pluto. So Pluto is in a 3-to-2 mean motion resonance with Neptune. So basically every time Neptune goes around the sun 3 times, Pluto goes around twice. This creates a phase protection. So Pluto's orbit is very stable, even though it crosses Neptune's orbit, because it will never cross Neptune's orbit when Neptune is there. So if it wasn't phase protected, it could even, say, impact Neptune or get ejected from the solar system due to interactions. The other really interesting thing about Pluto's orbit is Pluto always gets closest to the sun and crosses Neptune's orbit when it's far away from the ecliptic plane. So that basically also protects it from being ejected. And there are a whole lot of objects in the outer solar system, like Pluto, that we call Plutinos, that are in this mean motion resonance, but a lot of them are also in this pericenter resonance, which we refer to as COSI.
COSI.
Yeah. So I've been doing a lot, some work looking at basically the Plutinos that are in COSI and the Plutinos that are not in COSI to say, basically, did these objects come from the same parent population? Were they captured in the same way? Or is there something different about the way objects get into this pericenter locking than objects in the Plutinos as a whole?
So when you say capture, what do you mean?
Yeah, so if you look at the sort of distribution of objects in the outer solar system, you'll see these overdensity regions, and these overdensity regions correspond to mean motion resonances. Now, if you just imagined that the outer solar system just sort of formed the way it was, and Neptune always stayed where it is, there would be objects that formed in Neptune's mean motion resonances. But you wouldn't see this big overdensity because things would either just be in the mean motion resonance or they wouldn't. Basically, the large number of objects in these mean motion resonances is evidence for giant planet migration in the solar system. So Neptune migrated slowly out as it ejected planetesimals from the trans-Neptunian region inward, and then Jupiter threw most of those out into the Oort cloud. That basically sculpts the outer solar system. And there are a lot of clues in the distribution of objects in the outer solar system that can tell us, say, how fast Neptune migrated or how grainy the migration was. So I'm working with a team of investigators in the US and Canada and Taiwan, and we are trying to discover a lot of objects on Pluto-like orbits, and then figure out what their surface is like, so what their surface color is, and really nail down the specifics of their orbits. So we can better understand the distribution of objects in Pluto's orbit, with orbits just like Pluto. So one of the reasons we are doing a survey specifically targeting these is, as I mentioned earlier, Pluto always comes to pericenter, its closest approach, off the ecliptic plane. And so when it comes to pericenter, like below or above the ecliptic plane, they're harder to find because we look for TNOs on the ecliptic plane because that's where most of them are. So what we're doing is we are targeting regions of the sky where the Plutinos, like Pluto, which are in cosi, will come to pericenter, so above and below the ecliptic plane. So the discovery survey for the cosi Plutinos is run on the Canada-France-Hawaii telescope on Mauna Kea in Hawaii. So what we're doing with Magellan is we're trying to get the G, R, and Z band photometry. So basically, if you think about the sort of visual spectra broken into a rainbow, what we're doing is sort of lumping together parts of that. So sort of the blue end and the red end, and then the near infrared. And so we compare how bright the object is in those three band passes to try to figure out, whether the surfaces are the same as each other. Yeah, so we're hoping that we can basically nail down where the objects that are in this resonance formed. And then that will give us a lot of constraints on how Neptune captured them as well.
So what does a typical observing night at the Magellan telescope look like? So first of all, the Magellan is a 6.5 meter telescope in Chile, right?
Yes.
So do you need to travel there and get the observation yourself?
No, not anymore. So it used to be that the way all astronomy observing worked was you got a couple of nights and you got your students and you flew down and were shown how to operate the camera and then took the data yourself that night. The way most of it works now is it's taken by service observers who work at Magellan or other telescopes, and they take the data for you. So usually I go to bed and then in the morning I get an email that tells me, how the conditions were. But before I go to bed, I write up a very detailed plan. So basically what you do for specific sky conditions. So the data that I need basically needs, there not to be any clouds, and the seeing is low. So what that means is that if there's high winds in the atmosphere, it sort of shakes the light. So if you think about when you look at the stars and they twinkle, that's basically seeing. So you're seeing the atmosphere jiggle around the light coming from the stars. And we measure that numerically and call it seeing. So I need good conditions, which is no clouds and very little star jitter in order to take the data that I need. If those conditions aren't met, then I have some backup projects that they'll do instead. So before the night, I write up a very detailed plan with a list of all the targets and where they will be at what time. And then I send that to an observer, and then the observer takes that data for me. And when the conditions are good, then I just get a Google Drive link with gigabytes of data to download after the night.
Download, reduce, analyze.
Yes. Yeah, and then the real work comes in.
Yeah.
We discovered a very large comet.
Oh, good for you. It's headed directly towards Earth.
Is the population of Kuiper Belt objects still evolving today? Is there a chance that we will be hit by a trans-Neptunian object?
Yes, there's some evolution. So obviously there are still some collisions, although they're extremely rare because the Kuiper Belt is very low density. But mostly what we see is we have this population that we call scattering or centaurs. So these are objects that were in TNO orbits, but just aren't stable on giga-year timescales, so the lifetime of the solar system. These can actually get kicked into the inner solar system, and once they are inward of Neptune, we call them centaurs. And then once Jupiter dominates their basically their orbit. We call them Jupiter family comets.
Mhm.
Because when these objects come into the inner solar system, they become comets. They have a lot of ices on their surface that are not stable inward of 8 to 10 AU. So you may see, you'll see some low scale activity, probably driven by carbon monoxide. And then as they come further in, you'll actually get, water is no longer stable as it comes very close to the sun, and carbon dioxide. So you'll see jets and coma as these objects come in really close to the sun. These Jupiter family comets do impact planets sometimes. So, for example, Shoemaker-Levy 9 famously impacted Jupiter. It's not a really high probability event for the Earth to be impacted by one of these, but it is within the realm of possibility.
So how do you envision the future of Kuiper Belt exploration?
Yeah, so we're still unraveling sort of all of the really detailed information that we'll get out of New Horizons, the New Horizons mission, and there'll be a lot of really detailed geology and chemistry coming out of that, which will provide a really interesting context for understanding the bulk sample of TNOs. And the bulk sample of TNOs is about to increase really dramatically because the Rubin Observatory should be on Sky in the next few years, and it's going to run the Legacy Survey of Space and Time, or LSST. And LSST should discover tens of thousands of TNOs. And right now, we know several thousand, right? So we're talking about an order of magnitude increase in the number of known TNOs.
Wow.
And that's going to provide a really great sample, because not only is it going to discover them in a way that we can sort of understand how they were found, but it's also going to get data on them every night that it takes data. So you'll get measurements of how bright they are, how much their brightness varies, which means that we'll be able to see how they rotate. So if you think about something spinning and you see different faces towards you, if it's fatter, you'll see more light, right? So we call this basically a light curve, and from that we can say, what are the dimensions of these objects in general. And we'll also get color data. So LSST will be run in multiple bands, and when you observe it many, many times in multiple bands, you'll be able to figure out the colors of these objects as big bulk samples. So it's just really going to revolutionize what we understand about the distant objects. The other thing that's very exciting is the launch of JWST. So JWST is infrared optimized. And this sort of near-infrared region is where a lot of these lines for organic materials, as well as water ice and methane and nitrogen ice, these all are much, much easier to detect in the infrared bands than they are in the visual. So we'll be able to push our knowledge of what ices and what surface materials are on TNOs to a much fainter objects than we've been able to do in previous color studies.
Do you think there's any chance we'll have a sample return mission from the KBO?
I think it's pretty unlikely, right?
Okay.
So certainly within our lifetime, at the very least, maybe we could launch it, but you're talking something like 30 years to get out there, and then you have to come back. I don't think it's really likely, and I'm not convinced that it would be the best use of resources. It would be really interesting to basically send a space, like basically a laboratory, so something like a rover. So you can basically make some of the instrumentation we would use on Earth and put it on the surface of the object. And I think that would probably be a much, much better use of resources than attempting to bring back samples from the distant solar system. But we'll see. You never know what people can come up with really interesting ways to do it.
What object would you go to?
I think it'd be really cool to go to Haumea.
Haumea?
Yeah. So Haumea has it has a family. So basically, these are a bunch of objects that look like they were once part of Haumea. So we suspect that Haumea, at some point in the past, there was a giant impact on the surface and a lot of objects were ejected. And when that happened, it may have exposed sort of some of the inner layers of Haumea as well. So if you look at Haumea as it rotates, there's actually a red spot on the surface. So it'd be really interesting from a geological perspective to be able to sample multiple surfaces on Haumea and see how they compare. What I would like to see in the next Kuiper Belt mission would be an orbiter and a lander. I think that would be really exciting. And it might be time to go see another dwarf planet.